seismology. I hope you are aware of these fundamental concepts in engineering seismology. You know that Earth's interior is composed of four layers. The outermost layer is called crust, and then mantle, outer core, and inner core. And then the crust is further subdivided into two layers. The topmost layer is called as lithosphere, and a layer below lithosphere within the crust is called asthenosphere. Litho means stone, and sphere means layer, and astheno means without strength. So lithosphere is that part of the crust which is the outermost part of the crust on which we actually we are using this lithosphere, the outermost part of the earth crust, and it is a relatively rigid part, and therefore it is called lithosphere because it is like the stone, the stone sphere. And the steno without strength part is below the lithosphere, and lithosphere moves above asthenosphere. It is now a well-known fact that asthenosphere is a semi-fluid kind of state, and lithosphere, the harder part of the crust, moves above the asthenosphere and causing the movements of tectonic. Okay, the thickness of the crust varies above the continent. It is thicker, and within the ocean, it is thinner. And similarly, lithosphere also varies in thickness from around 5 to 8 kilometers up to 100 kilometers, and so on. You also know that most of the earthquakes occur at the boundaries of tectonic plates. The Earth is composed of several plates, big plates around 7, and then there are many small plates, and the plates are moving. The lithosphere part of the crust is moving above the asthenosphere. And while these movements are taking place, somewhere the plates are converging toward each other, where they are colliding with each other, and there is a head-on collision. And at some points, they are moving away from each other, and somewhere they are sliding against each other. The boundaries are the location where the two plates are converging. These boundaries are called convergent boundaries. An example of this is this one, this convergent boundary. This is a convergent boundary. And where the plates are moving away from each other, then the boundary is called as divergent boundary. And when they are sliding against each other, the boundary is called as transform boundary. Earthquakes occur most commonly at the convergent boundaries and transform boundaries. If you look at this part of the Earth, so this is basically the Indo-Australian plate, and in front of this plate we have Euro-Asian plate. And Indo-Australian plate is moving towards north, whereas the Euro-Asian plate is moving towards south, and thus thereby forming a convergent boundary in the Himalaya range. And while they are locked against each other, the strain energy will be stored in the crust, and when there is a sudden rupture of the crust at any location, particularly at the fault locations, then the energy is released in the form of earthquake waves, causing movement of the ground. Okay, and you can see that these dots basically show the frequency of the occurrence of earthquakes. You can see a number of dots along the Himalaya range. Similarly, we have these boundaries where the plates are moving against each other, transform boundaries. However, at the divergent boundaries, earthquakes do not occur because there is no release of energy at the divergent boundaries. So these are the Now, this is a well-known fact that earthquakes occur at the boundaries of the tectonic plates. However, it is possible that some earthquakes occur within the plate, which are called as intraplate earthquake. And these earthquakes which occur at the boundaries of the plates are called interplate earthquakes. Okay, once a rupture occurs deep down the earth crust, then the energy travels in the form of earthquake waves. And when the energy reaches the surface of the earth, then the waves will travel on the surface of the earth, and finally, when they come across a building, then the building which is resting, the foundation of the building which is resting on the ground, and when the ground moves due to the earthquake movement, ground motion, then the ground and the foundation will move by the same amount of displacement. However, the rest part of the superstructure attached to the foundation will not be able to move with the same displacement as of the ground because of the inertia forces. Due to inertia, the superstructure will lag behind, because the inertia is the property of material due to which it tends to stay in its original position. Due to the inertia, when the superstructure tends to stay at its original position, relative moments will occur and stresses will be induced in the structure, and which may cause collapse of the structure. Okay, the point within the crust, deep down the earth crust, where actually a rupture occurs, is called as focus. This is the point from which energy is actually released and travel in all direction. The projection of this focus on the surface of the earth is called epicenter, and the depth is called focal depth. The distance from the epicenter to the object or place of interest or building is called as the epicentral distance. In this figure, the earthquakes have been shown by dots along the boundaries of the tectonic plates. You can see that mostly earthquake occurs at the boundaries of tectonic plates. In this slide, we have shown different types of waves. I hope you know these types of waves. You would have studied this in engineering seismology. There are two types of waves, basically body waves and surface waves, and each of them can be then further subdivided into two types. P waves is the type of body wave, which is called a push and pull wave, compressional dilation wave, and S wave is a slide to side or shear wave. Surface waves are also classified into two types, love waves and Rayleigh waves. Their movement is slightly different, and they are mostly travel on the surface of the earth. Okay. Okay, no matter what type of earthquake wave hits a building, whenever it hits a building at the base of the building, because the foundation of the building is basically in direct contact with the ground. So when the ground moves due to the earthquake waves, then the foundation will also move with the ground. But because foundation is attached to the superstructure, so the superstructure should also move with the ground. But due to inertia, the superstructure and the roof of the structure, the wall, they cannot move by the same amount of displacement as that of the ground or foundation, and thereby due to inertia. So when the superstructure lags behind the foundation, it produces stresses in the foundation. It produces stresses in the lateral load resisting elements, which are walls and columns, are both of them. Okay, so if foundation, when foundation moves with the ground and the superstructure is capable of moving along with the foundation by the same amount of displacement as of the ground, then there will be no stresses induced, for which the structure must be very, very rigid, very stiff. The height will be small, and the stiffness in terms of the wall thicknesses and length shall be very high, and only then the structure can move, the superstructure can move with the foundation, and that motion is called basically rigid body movement, rigid body motion, rigid body movement. And in that case, no stress will be induced. On the right, there is another example where the columns have been showed, and these columns are attached to roof and to the foundation. When ground moves, the foundation also moves by the same amount as that of the ground. The ground movement and the foundation movement is the same because the foundation is directly resting on the ground. However, when this movement is transferred to the roof level, due to inertia, the roof will not be moving by the same amount of displacement, and also because the roof is attached to the foundation through these flexible, relatively flexible elements. So it will not be possible for the roof to move with the foundation by the same displacement. So when the foundation moves by the displacement, let's say 3 inches, and the roof moves by a displacement, let's say 1 inch, there will be relative displacement of 2 inch, and this relative displacement is basically responsible for producing stresses in the structure. If there is no relative stress, which means that if the foundation displaces by 3 inches and the roof also displaces by 3 inches, relative displacement is zero. This will be kind of rigid body movement. No stress will be induced in columns or walls. So with this concept, we can see that if we are able to design our structures or to propose and proportion our structures in such a manner that the displacement of foundation and the superstructure is same. However, practically it will be almost impossible to proportion such structures because the vertical the members like columns and walls need to be very, very stiff, and they'll become too uneconomical. For very low-rise structure, let's say 10 feet or 8 feet high structures, one-story, single-story, it may be possible in some cases, but in most of the practical situation, it will not be possible. And one other possibility of avoiding stresses in the columns and walls is that when foundation moves, when the ground moves, foundation should stay at its original position, and this can be done only when foundation is attached from the side. This can be done through some technique by placing some soft material, which is some kind of lubricant or some other soft material between the foundation and the ground. So when the ground moves, the foundation does not move with the ground. So which will give rise to basically a concept called as base isolation. Base isolation can be done in many ways. Base isolation and making a structure very rich, very, very rigid, so that relative displacement does not occur, are two techniques which can be used to prevent the stresses, the formation of stresses in walls and columns. Okay. If we cannot do either of this, then we must design our structures such that these stresses do not collapse, do not cause collapse of our structures. Okay, when an earthquake occurs deep down the earth crust, then earthquake waves will travel in all directions. However, these waves, the vectors of these forces arising from the earthquake waves can be resolved into three components, X, Y, and Z, along the geometric axis of the building for our own convenience, and which means that the building will move in the X and Y direction as well as in the Z direction. Z direction is the vertical direction, and X and Y are horizontal direction. X and Y movement is very obvious that it will cause the horizontal movement of the building, and as I explained earlier, that when the ground moves, the foundation will move, and the superstructure will not be able to move along with the foundation by the same amount of displacement. So it will cause stresses when the structure moves either along X or Y direction. Okay, the structure will typically move not along the geometric axis, but along any direction, maybe somewhere between the X and Y. But however, for our own convenience, we will be able to resolve all these into all these motions. The motions will basically give rise to some forces, and then the forces can be divided into X and Y along the geometric axes of the building in order to calculate the stresses in the building. The vertical direction Z, the vertical acceleration during ground shaking either will aid to or subtract from the acceleration due to gravity, because you know that when the structure is at rest, there is a G acceleration acting, gravitational acceleration acting downward, and the total weight of the structure is calculated from the mass of the structure multiplied with the gravitational acceleration. So W becomes M times 1G. And you also know that acceleration due to earthquake are some fraction is some fraction of the gravitational acceleration. And so if the gravitational acceleration is 1G and vertical acceleration due to the earthquake waves is, let's say, 0.2G, then when the direction of the acceleration is upward, the inertia or the forces M times acceleration of the earthquake waves is upward, then the weight of the structure at that instant of time will be total weight W is equal to mg minus 0.2 mg. So the weight of the structure will be reduced by 20% when the acceleration direction is upward. However, when the acceleration direction is downward during an earthquake event, then the weight of the structure will be increased. Normally, in today's engineering design practice, we design our structures, or we analyze our structure along X and Y direction for the earthquake forces, and the Z direction is indirectly taken into account because, as I said earlier, the vertical acceleration along Z direction will either increase the weight of the structure or decrease the weight of the structure at the same instant of time when it is being hit along X and Y direction. So what we do is that we apply forces along X and Y direction at that particular instant of time when it is being hit by the earthquake. At the same time, we also reduce and increase the weight of the structure to see the maximum effects in the structure. Okay, something on the types of earthquakes with respect to focus. You know that there are basically two types of earthquake with respect to focus. If depth of focus varies between 0 and 70 kilometers, they are called as shallow earthquakes. And if they are deep, between 70 and 700 kilometers, they are called as deep earthquakes. Okay, the characteristic of earthquake waves with respect to distance from epicenter. This is one of the important concepts in earthquake engineering. When an earthquake occurs, so within the 25-kilometer range from the epicenter, there is a field which is called as near field in this circle, which is shown here in this circle from this yellow dot, which shows basically epicenter, and this is the epicentral distance. So within this 25-kilometer of epicentral radius, the field is called as near field. Yeah, this location is called as near field location or near field region. And the earthquake waves, when travel from the epicenter, they will have different characteristic in different region, and this characteristic will change with distance. Within this near field region, from 0 to 25 kilometers, the earthquake waves characteristic are such that their duration is long and their frequency is very high, amplitude is also very high. So within the near field region, the amplitude and frequency are high and the duration is long. These are the characteristic of earthquake waves within the near field region. The range of the frequencies is 3.33 to 20 hertz, and in terms of time period, the time period of the earthquake waves are that the time period of the earthquake waves ranges from 0.05 to zero point 0.3 seconds. You know that earthquake waves are not sinusoidal in nature, and they cannot be represented by a particular function. They are random in nature and they have a range of frequencies. However, within the near field, the range of frequencies will be such that the time period of these waves will be varying from 0.05 to zero point 0.3 seconds. And so there will be very short period and high frequency waves, and their duration will be long, which means that they will keep on vibrating uh, for a long period, and their amplitude will also be high. They will be very vibrant. And within another region from 25 to 50 kilometer, the range is called as intermediate range or intermediate field. So when the earthquake waves are uh, within this region, 25 to 50 kilometer, when their characteristic will change, their frequency will attenuate, will decrease from uh, 3.33 to 20 hertz to 3.33 to 1 hertz. Now 3.33 is the highest frequency and 1 hertz is the lowest frequency. In terms of time period, the time period will now increase, and the range of time period will be 0.3 to 1 second, which means that they will now be less vibrant, uh, and uh, similarly, the amplitude will also be less, and the duration will be short as compared to the near field region. Okay, so the earthquake characteristic will change with distance from the epicenter, and the frequency and amplitude both will keep on decreasing with distance, which is called as attenuation of the frequency and attenuation of the amplitude. And the duration will also keep on decreasing. So, for example, if you have a recording instrument and you record an earthquake near the epicenter within the near field region, it may be 30 seconds, but in the intermediate field, it may be 29 seconds, 28 seconds, or 27 seconds, will be shorter than what is recorded within the near field region. Excuse me. Sí, sí. Das machst du. So, Rodolo sì, le può usare. Okay. Then after the intermediate field, there is another region which is beyond 50 kilometers, and that is called as far field region. In the far field, the earthquake waves, characteristic of the earthquake waves further change. further attenuate, the time period range becomes from 1 to 10 seconds, and the amplitude will also be less in the far field region. It will be less vibrant, less vigorous, and the time duration of the earthquake will also be short. So these earthquake characteristics are very important to understand because when a structure is located in the near field region, so the time period of the structure, you know that every structure has a fundamental time period. So if the earthquake waves have some range of time period, and if any of these time periods can match with the time period of the structure, a resonance can occur, and it will be fatal for the structure. So with this concept, now we move ahead with the structural time periods. What are the ranges of the structural time periods, and how the match in frequency is possible, and how the resonance will occur, and what will be the effect of this resonance on the structure. You know that the natural time period of a structure is an important characteristic to predict behavior during an earthquake of certain time period, which is called as resonance phenomena. For a particular structure, the natural time period is a function of mass and stiffness. For a heavily loaded structure or a heavy weight structure with less stiffness, time period will be more. However, time period can also be roughly estimated from time period equal to 0.1 into number of stories general structures. Okay, now overlapping the frequencies of, or comparing the frequencies or time period of the earthquake waves to the time period of the buildings, and let's look at the situations where the resonance can occur. So as we said in the last slide, that the time period can be calculated from time period is equal to estimated roughly 0.1 into number of stories. So low-rise structures up to 3 stories would have time period from, let's say, 0.1 to 0.3 seconds. 0.1 to 0.3 seconds. And you know that the earthquake waves time period within the near field region will also vary from 0.05 to 0.3 seconds. So the probability of occurrence of resonance will be very high for low rise structures if they are located in the near field region, as compared to the structures which are higher than 3 stories. So low-rise structures will be susceptible to more damage if they are located in the near field region than the structures, than the high-rise structures. Okay. However, it does not mean that high-rise structures will always be safe in the near field region. The resonance, the occurrence of resonance and non-occurrence of resonance does not necessarily mean that the low-rise structures will be low-rise structures will always collapse and high-rise structures will always be safe. It only means that the possibility or probability of occurrence of resonance for low-rise structures is very high in the near-field region, and for high-rise structures or medium-rise structures, this probability is low. However, when resonance occurs, you know that when resonance occurs, the amplitude keep on increasing, and when this amplitude of the structure or the drift of the structure reaches a level where it exceeds the capacity of the structure, then the structure can collapse. So resonance is no doubt dangerous, but resonance with sufficient energy imparted to the structure is also necessary to cause damage to the structure. So this can be explained through a very simple and very well-known example of soldiers crossing a bridge. You would have heard this example several times, that when soldiers cross a bridge, their footsteps can produce some time period, and if the time period of the footsteps of soldier is equal to the time period of the bridge, because when the bridge is vibrated, so during its free vibration period, it would have a time period. Time period can be calculated, which is the time required to complete one full cycle of vibration. So if that time period is equal to the footsteps of the soldiers, then resonance will occur. But it does not mean that if there is only one soldier, he will also be able to collapse the bridge, because the energy imparted by one soldier will not be enough to cause damage to the structure and uh, to push the structure to a level where the capacity of the structure will be exceeded by the stress due to the energy imparted in resonance. If there are enough number of soldiers, and if their frequency a time period of the footsteps, they become equal to the time period of the footsteps of the soldiers at any instant of time, becomes equal to the time period of the fundamental time period of the bridge, then resonance will occur. And then the collapse will not occur when the resonance occur, but resonance will cause the resonance will keep on increasing the amplitude or the displacement of the bridge. And when this displacement of the bridge reaches a level where the capacity of the bridge is exceeded, then the bridge will collapse. Similarly, now in another situation opposite to this, if there is no match of the if there is no match between the time period of the footsteps of the soldier and the bridge, what will happen? In that case, uh, it is possible that when there is no resonance, when there is no absolutely no resonance, so there is no doubt that it is a good situation. However, if there are too many soldiers, and if they hit the bridge in the first instant of time, in the first step when they push the bridge down, it is possible that at that instant of time, during this impulse force, they collapse the bridge. So this is possible. So by this explanation, I mean to say that even when there are some high-rise structures located within the near field region, so the impulse force, the first hit of the earthquake can cause collapse of the structure, although there will be no resonance occurring during this motion. Now, coming to the medium rise structures, in the medium rise structures, the same concept is applicable, that up to 5-story structures, the time period will be 0.4, 0.5, or 0.6. And within this range, within this region, intermediate field, the earthquake time period also varies from 0.3 to 1 second. So if the frequency or time period of the earthquake waves matches with the frequency or time period of the building, then resonance will occur and the buildings may collapse if their capacity exceeds the stresses induced in the structure. The same is applicable to high-rise structures. So the conclusion is that low-rise structures are more susceptible to get damaged. They are located in the near field region. Medium-rise structures similarly are susceptible to more damage if they are located in the intermediate field, and high-rise structures are more susceptible to damage when they are located in the far field region. Earthquake recording is done through seismographs. You might have studied seismographs in your engineering seismology courses. This is one of the seismographs shown in the figure, typical seismographs. Using multiple seismographs around the world, accurate location of the epicenter of the earthquake as well as its magnitude or size can be determined. And the working of a seismograph is shown in the figure. This is a seismogram, a record obtained from the seismograph. You know about the Richter scale. Richter is the name of the scientist who developed this scale. In 1935, The Richter scale is logarithmic in nature. That magnitude 5 Richter measurement is 10 times greater than a magnitude 4, while it is 100 times greater than a magnitude 3 measurement. These things. Just for the sake of completion, we have included these basic concepts in our lecture. These are some of the records that have been recorded, earthquake records around the world. On the top left, there is a famous record called as El Centro 1940 record. This record is famous because this record is mostly used in experimental testing. We in our university also use this record in our testing, shake table testing, because this record is digitally available and it has a frequency component and amplitude, which is mostly required in low-rise structures. So it is best suited for the experimental testing of low-rise structures. There are other records also available. For example, on the top right is the Barfield earthquake, the San Fernando earthquake, and the other earthquake Northridge is also a famous record. At the bottom of this figure, you can see a very different type of earthquake record, which was recorded in Mexico City in 1985. And this is a very classical example of a record obtained in the far field region. All other records are obtained in the near field region. You can see that the records which are obtained in the near field region is very high frequency component, very high amplitude and long duration. However, in this Mexico City record, which was recorded in the far field region, the frequency is very low, the time period is high, and similarly, the amplitude is also very low. This is also a very classical example of the damage caused by this earthquake, by this type of earthquake to the high-rise buildings. This record was obtained around 350 kilometers from the epicenter, and many buildings got damaged. Some of them collapsed due to the frequency match or resonance phenomena between the earthquake waves and the building frequency. So this is a classical example, but this is only one example around the world which can be demonstrated to show resonance occurring in a far field region between the high-rise building and the earthquake waves in the far field region. Okay, these are the earthquake occurrence around the world. You can see the magnitude on the left, 2, 3, 4, 5, 6. These are the magnitude and Richter scale. And then on the right, this energy release in terms of equivalent kilograms of explosive. A magnitude 6 earthquake will release energy, roughly speaking, equal to Hiroshima atomic bomb, and the frequency of the number of earthquakes that occur per year worldwide is 200 of magnitude 6. And with the increase in the magnitude, the number of earthquakes per year decreases. We have only 3 earthquakes of magnitude 8 or so. Many of these earthquakes occur in the ocean, thereby not causing any damage to the continent part. However, whenever they hit the continent part, you see that a lot of damage occur to the buildings. This is the seismic hazard zoning map of Pakistan. The seismic hazard zoning map of Pakistan is divided into 4 zones, and zone 2 is then further subdivided into 2 zones, zone 2A and 2B. Okay. The zone in the order of increase is in the ascending order, the severity of the zone increases. So when we say that zone 1, so zone 1 is a zone where the earthquake acceleration, the expected earthquake acceleration will be very low, and this is a low seismic hazard zones. So earthquake will be, the frequency of the earthquake will also be very small, and the frequency of occurrence of earthquake, not the frequency of earthquake waves. and building will be least affected when they are located in seismic zone 1. Seismic zone 2A and 2B are moderate seismic zones. Seismic zone 3 and 4 are high seismic zones. Zone 2A are called low, moderate, and quick zones. Now, coming to the regions, you can see that Khyber Pakhtunkhwa is located in zone 2B mostly, with the northern part in zone 3. Some parts are also in zone 4, Balakot and Chitral. Punjab is mostly located in zone 2A, and Balochistan is also like Khyber Pakhtunkhwa located in the zone 2B, 3, Quetta and the surrounding regions are in zone 4. Okay, parts of Sindh are located in zone 2A, 2B, and the subduction zone near Karachi is also in zone 4. Okay, importance of architectural features and their effects on buildings. There are some desirable shapes and some undesirable shapes. By desirable shapes, we mean that if the shape is desirable from the structural point of view, then designing and construction of the structure will be economical. However, if the structure is of undesirable shape, then it will be costly to design and construct that building. So too tall building, too long and too large and plain, these are undesirable shapes. These are simple planes, they are desirable, these are desirable shapes, these are undesirable shapes. T, curve, and L shapes, they are not good shapes. If the NL shapes are required, so it is better to keep some gap between the two buildings. And these separation joints or gaps are called as seismic gaps. They will allow the buildings to vibrate in their own mode instead of overlapping modes if this is in L shape. So at the planning stage, architects and structural engineers must work together to ensure that unfavorable features are avoided and a good building configuration is chosen. It does not, however, necessarily mean that if a structure is of bad shape, it cannot be designed. It can be designed, but will be uneconomical. These are some other undesirable situations where the two structures are located very close to each other. These adjoining buildings can hit each other, and the pounding action can cause localized collapse or localized damage to the structure like this thing. Similarly, if the structures are located on a slopy ground, on hanging or floating columns like this, is also not good. And discontinuing structural member like this is also not good. A typical situation in buildings is a situation where the basement stories or ground stories are kept for parking with no walls, and the upper stories are provided with masonry rigid infill walls, thereby making the upper stories more rigid, more stiff than the lower stories. So when there is an earthquake, the building will move in this manner. The lower part of the structure will move more than the upper part, and this story is basically called as a soft story, and these soft stories need to be avoided in structure. However, if soft stories are to be there, because there will be a requirement sometimes for parking in these parking requirements in the basement and ground stories is a requirement of a building. So they cannot be avoided. However, they shall be taken into account in the design. And the building shall be designed in such a manner that displace this will create problems in the structure. When engineers analyze the structure, they must keep into account these rigid walls. And when these rigid walls are taken into account in soft stories, effect is taken in the design, and there will be no problem. However, the building will be slightly uneconomical if there were no difference in the intermediate stories stiffness is happens in the case of soft stories. Next is the earthquake design philosophy. In the earthquake design philosophy, we will try to explain how do we design our buildings against earthquake forces? How should we design our buildings against earthquake forces? For example, one can say that we should design our buildings against earthquakes such that no crack occurs in the building. Other can say that, okay, we will allow some cracks and so on. So you know that earthquakes do not occur very frequently. Some of the earthquakes do occur very frequently, but some of the earthquakes of large magnitude, they occur as you have seen in the frequently. Therefore, undamaged when they are being those frequent earthquakes are of low magnitude, and the building, if the building is allowed to get damaged due to the rare earthquakes, whose are of relatively larger magnitude, and they occur once in the whole service life of the structure. So, and if the damage is recoverable or repairable, then I think it will be an economical approach, because in order to design structure so that it is always undamaged when hit by any earthquake, it will be too uneconomical, and the initial investment will be too high. It will almost be not affordable even for very rich people. So with this explanation, now we try to explain the concept of earthquake design philosophy. And in this figure, on the figure on the left, and then on the y-axis from top to bottom, we have earthquake, different types of earthquakes. The first earthquake here, the first type of earthquakes are those earthquakes where the possibility of probability of the occurrence of earthquake is 50% in 50 years. They are very frequent earthquakes, but fortunately they are of low magnitude. And then we have rare earthquakes, those earthquakes where the probability of occurrence is 10% in 50 years. In other words, it means that the probability of non-occurrence is 90%. So 90% there is a chance that earthquake of this magnitude will not occur. And then very rare earthquakes are those earthquakes whose probability of occurrence is 2% in 50 years. And in other words, it means that the probability of non-occurrence is 98%. So it will not be advisable to design our structures for an earthquake event whose probability of non-occurrence is 98%, such that buildings do not damage, buildings remain undamaged during this earthquake. It will be too uneconomical, too costly. Okay, then depending on the operational level, we have a fully functional building when they are being hit by an earthquake, operational level, life safety level, and near collapse level. These different types of performance levels are explained in the figure on the right. With fully functional means that everything is perfect, no problem in the structure. Operational means that some damage has occurred, but still the building is operational. Life safe is a level where life safety is there. The occupants of the buildings are safe, and the building is in such a condition that it is damaged, but this damage can be recovered or repaired, which is called as retrofitting. Near collapse is a level, a performance level, where although life is safe, though small injuries can occur, but the building is not recoverable. The building needs to be demolished after the earthquake. It is not possible to retrofit the building. Okay, so on the x-axis on the top, we have performance level from fully functional to near collapse. On the y-axis, we have different types of earthquakes. And now coming to these three lines. On the top line, top inclined line, we have performance of our ordinary buildings. ordinary buildings. And then we have performance for essential buildings. Essential buildings are primarily, it will depend on country to country and place to place, uh, they which buildings they place in the essential building type. However, generally speaking, schools and hospitals and some of the important public buildings, they are placed in the essential building group. In the performance for hazardous facilities, nuclear power plants and plants or industries which produce hazardous chemicals, they are included in this category of buildings. Now, coming to the performance of ordinary buildings. If a building is ordinary, so it should remain operational when it is being hit by very frequent earthquake, but need not to be fully functional, which means if there is small glass breakage or something, so it is okay, we can live with it, we will repair this after the earthquake. Okay, and for rare earthquakes, whose probability of occurrence is 10% in 50 years, and 90% non-occurrence, the ordinary building shall remain at life safety level, life shall be safe. The essential building shall remain operational because due to these earthquakes, if essential buildings are also not at operational level, then it will be very difficult for the uh, people who will be working after the earthquake. Evacuation will be difficult in the placement of people from damaged building to the buildings which are operational. Schools, buildings, hospital buildings, and other public buildings should remain operational. Okay. However, the nuclear power plants shall remain fully functional even when the earthquakes occur, those probably remain operational. You would have heard a recent incident of a lot of damage to the surrounding areas, radiations. So the nuclear power plants shall remain operational when they are hit by very earthquakes, but the essential building shall remain at life safety level, which means they can be repaired and they can be restored to their pre-damaged state. However, the performance for ordinary buildings will be such that when they are being hit by very earthquakes, they'll be near collapse level, which means it will not be restorable and they will be demolished. So with this design philosophy, we design our structures so that the structures are economically designed. Building Code of Pakistan. Now, in Pakistan, the design criteria for quick loading are based on design procedures presented in Chapter 5, Division 2 of Building Code of Pakistan, Seismic Version 2007, which have been adopted from Chapter 16, Division 2 of UBC 97, Volume 2. Okay. The Building Code of Pakistan, I was one of the members of the Building Code of Pakistan. The Building Code of Pakistan was developed in 2000 after the 2005 earthquake. It was for the first time published in around 2010. The Building Code of Pakistan is more or less the same as UBC 97. UBC 97 is an American code with the name Uniform Building Code, published in 1997. The reason for adopting UBC 97 as Building Code of Pakistan was that at that time in 2005, UBC 97 was the most used code in Pakistan, and the parameters which are needed for the design of buildings, they are available in Pakistan very readily. And later on, UBC 97 was completely replaced by another code called as IBC, International Building Code. International Building Code cannot be adopted by building code of Pakistan because the IBC requires several parameters, design parameters, which are not readily available in Pakistan. We do not have data for those parameters. Recently, Pakistan Engineering Council is making an effort to bring building code of Pakistan in line with the IBC, and these parameters will be locally developed by a group of researchers. We at UAT also have a group, and we are working with them to produce these to develop these parameters so that we can update building code of Pakistan. Okay, the lateral force determination procedures in the building code of Pakistan are UBC 97 is such that the total design seismic force imposed by an earthquake on the structure at its base is referred to as base shear V in the UBC 97. If you remember in one of the slides, I was trying to explain to you that the total push at the base of the structure, by the earthquake when the earthquake waves hit the foundation of the structure, the foundation along with the ground will move, but the superstructure cannot move by the same amount of displacement, thereby causing relative displacement and stresses. The structure must be designed to withstand those stresses, and at the same time, some damage will be allowed. So this analysis can be done using the UBC 97 procedure. There are two procedures currently in the code. One is called as dynamic lateral force procedure, which is covered in section 1631 of UBC 97 and section 5.31 of the BCP 2007. As I said earlier, that building code of Pakistan, except the seismic hazard zoning map and seismic hazard zoning parameters, is more or less the same as UBC 97. So the sections are also same. Only 16 is being replaced by 5. So this 1631 it is 5.31. Static lateral force procedure is another procedure. There are two procedures, dynamic and static. Both are allowed in the code, and they are applicable in their specific situations. The dynamic lateral force procedure is then further subdivided into two types. One is called as time history analysis, and the other is called response spectrum analysis. I'm not sure whether you have studied these type of analysis in your dynamic course or not. However, if you not study the dynamic course, you will study this course, and I hope these two types of dynamic procedures, dynamic lateral force procedures, are taught to you in your structural dynamics course. We will briefly discuss how these procedures are applicable in our context. In the time history analysis, the digital data in the numerical form is applied to the foundation in the form of ground acceleration, and then the response is calculated in the form of displacement U over the whole history or duration of the earthquake. And for this reason, it is called as time history analysis, because it gives you the response of the structure at every instant of at every corresponding instant of time during the history of the earthquake. So if this is the history of the earthquake or record of the earthquake, at every corresponding instant of time, you will get a displacement in this form. Okay, so you exactly know where the structure is going during this earthquake. And obviously, this is an earthquake which is going to happen in future, and the record of the earthquakes that we will be using for this analysis are obtained from the previous earthquakes. So we cannot predict 100% accurately the response of the structure for future earthquakes. But keeping in view all the statistical combination and permutation, we make some use of our statistical knowledge in order to predict the behavior of the structure for future earthquakes. So for this purpose, either artificially generated earthquake records are used, or records of the past earthquakes are used, and then they are modified according to the soil conditions and other requirements. And then the response is calculated numerically in this form. This is a very laborsome and time-consuming analysis, it's not possible to be done for every structure. This is only this type of analysis is only done for very important structures, because of the complexity involved in the procedure. Okay, instead of time history analysis, there is another procedure which is also dynamic, but is much easier than the time history analysis. And the concept of the response spectrum analysis is that every structure has every structure has a time period, and a structure can be represented by a time period. For example, when I say that the time period 0.3 seconds, so there will be a group of structures having time period of 0.3 seconds, regardless of the material of the structure. For example, let's say the structure may be masonry, maybe reinforced concrete or steel structure, but this is possible that with different proportions of their different components, they have a time period of 0.3 seconds. Well, so when we say that the time period of 0.3 seconds for a structure, it means there is a group of structures whose time period will be 0.3 seconds. Similarly, 0.4, 0.5, and 0.6 seconds time period, every structure would have some time period. So the time period from the time period of the structures, if we calculate the response of that structure for a particular input time history in the form of ground acceleration, we can plot this on a graph with the time period on the x-axis, here. So every time period will basically represent a structure, and on the y-axis, the peak response of the structure will be plotted. So, for example, for a time period of 0.3 seconds, if we apply time history, so the time history will give us the response of the structure, and this peak of this response will be noted, and this peak of response will be plotted against the time period of 0.3 seconds on this graph. So, 0.3 seconds and t, let's say d1. Similarly, for another time period, again repeating this procedure of time history analysis, another peak, another peak, another peak. You can see that with the increase in time period, the peak displacement decreases, and the reason for this is that most of these records which we use in the time history analysis are obtained in the near field region. So they have a frequency component which matches with the low rise structures, and thereby causing resonance in the structure and giving us more displacement. So for this reason, when the time period is low, then the response will be more, because the frequency 0.3 second, a time period of 0.3 second will match with the time period of 0.3 second, which exists in the near field region record. Similarly, here the same record is used because all the records which are obtained in the near field region, it is a common practice in earthquake engineering that records obtained from the near field are used in time history analysis. Although the most recent codes also insist on using some records obtained from far field region for the analysis. So this will give rise to a graph like this response spectrum. This graph is called as, this plot is called as response spectrum plot or response spectrum curve. A typical response spectrum curve exists in UBC 97 in Building Code of Pakistan, which has three different types of branches. This branch is an ascending branch going from this to this. Then we have flat portion and then descending branch. And with these parameters, this response spectrum can be calculated. So response spectrum procedure is easier than the time history analysis because you just have to calculate the time period of the structure and then get this maximum displacement from the response spectrum, and then calculate the forces from K times displacement, and from this force you can then further analyze your structure and calculate the stresses and bending moments and add these bending moments to the gravity load bending moments. Okay. Before we discuss the static lateral force procedure, the calculation of static lateral force procedure, this slide will give you an understanding or concept of the static lateral force procedure. I said quite a few times today to you that when ground moves, the foundation attached to the ground will also move along with the ground, but the superstructure, due to inertia, cannot move by the same displacement. It will lag behind, causing these stresses in the walls. These stresses shall be of such a magnitude that they shall be less than the strength of the structure or capacity of the structure in order avoid the collapse of the structure. Okay, so this you can see that the base and apply a force at the top, at the roof level, produce almost the same effect. I can produce almost the same effect. So this effect can be produced. It is possible to produce the same effect. Step is to calculate the push at the base, which is called as the base shear. And because the base shear, the push at the base will depend on the earthquake uh, magnitude, earthquake force, in other words, in the zones in which the building is located. So CV is the seismic coefficient, which depends on the zone in which the building is located. CV will be taken from the tables, seismic hazard zoning map. I is the importance factor. For example, if a building is very important, like essential building, so this I will be more for the building, so we will be more, and stresses will be more, and we will be designing the building in an higher performance level. However, if I is 1, then it will be considered as normal design, normal building. R is a numerical coefficient which represents basically an inherent overstrength and global ductility capacity of lateral force system. And R will be explained in the coming slides in detail. T is the time period of the structure, and W is the weight of the structure. So CVI divided by RT, which is called as base shear coefficient, and W is the weight of the structure. This multiplied by, so the greater the weight of the structure, the greater will be the base shear. And the greater the base shear, the greater will be the forces, and then the capacity of the structure need to be increased in order to overcome the stresses produced due to these base shear. Okay, the other equations, this is the basic equation. Other equation for the other equations for the base shear are, this is the maximum base shear equation, 2.5 CIR divided by W. And on the response spectrum, basically this represents the flat portion of the response spectrum. So base shear need not to exceed this value. The base shear shall not be less than this value for seismic zone 1 to 3. And for seismic zone 4, this is an additional check. Another base shear equation will be equal to 0.8 Z NBI R divided by W. Okay, NB is the near source factor, which is obtained from table 16T. Okay, next we will discuss the steps for calculation of V, base shear. In step 1, we will find the site-specific details. In step 2, determine seismic coefficients. In 3, determine seismic importance factor, R factor, structural time period, base shear, and so on. We will start with the step 1, site-specific detail. In site-specific detail, seismic zone in which the building is located shall be determined from the seismic hazard zoning map. For example, if the structure is located in seismic zone 2B, so it will be in this region, let's say in KP. So the seismic zones, once we know the seismic zone in which the building is located, for example 2B, We'll go to the table and seismic zone factor. This table, seismic zone factor, tells us about the Z factor. For zone 1, it is 0.075, for 2, 8.15, for 2B, 0.2, for 3.3, and for zone 4, it is 0.4. So we'll get this information from this table 16I. Once we get this information from the table 16I, then we will need the information on the soil type. There are 5 basic soil types: SA, SB, SC soil, SD stiff soil profile, SE soft soil profile. And the shear wave velocity can be determined in the field, or SPT can be determined, and they can be correlated to determine which type of soil is the one where the building is to be located, where the building is to be constructed. And then we have underhand shear strength. So with this, we will be able to know the soil type. Once we have this test data, there is no okay sites further in site specific details. If we are working in zone 4 particularly, then other information is also important, which is the past earthquake magnitude. This is required only for seismic zone 4, as I said earlier, to decide about seismic source type, so that certain additional coefficients can be determined. So a seismic source type A will be that seismic source where it can produce earthquake with magnitude 7 or larger, and the slip rate of the tectonic plate is 5 millimeter per year. So they are classified as seismic source type A, seismic source type B. Similarly, seismic source type C, they are also classified according to the magnitude. The maximum moment magnitude which has occurred in past or is expected in future, and the slip rate. So this type of seismic source type need to be known to us if we are designing a building in seismic zone 4 only, and then to be known to us. So the next is the distance to the epicenter. This is the seismic coefficient CV of corresponding to soil type and Z factor. So once we know the Z factor and soil type, for example, let's say our soil type is SD and we are working in zone 2B. So corresponding to seismic zone factor Z, the CV coefficient, which is used in the basic equation corresponding to SD type soil, is 0.4. Okay. NV factor, which we were discussing in the last slide, this will depend on the distance from the epicenter and the seismic source type. For example, let's say the seismic source type is A, the building is located in the near field, and the seismic source type is such that the earthquake events of magnitude 7 or larger can be produced in that location, and the distance from the epicenter is less than 2 kilometers, so this factor will be 2, which means that the base shear will be doubled as compared to the base shear calculated in other zones. Similarly, 5 kilometer, 10 kilometer, and beyond 15 kilometer, this factor will become 1. Similarly, there is another factor CA which is required in the equations, as you will see in the example. This can also be calculated from table 16Q. SD type soil corresponding to SD type soil, seismic zone factor is corresponding to seismic zone factor of 0.2. The CA is 0.28. Similarly, seismic source type A and A factor can be calculated with a distance of 2 km, 1.5, 1.2, and so on. Important factor, as I said earlier, for essential building it is 1.25, and for ordinary building it is 1. R factor. R factor basically reduces base shear because it is in the denominator. So it reduces base shear V to make the system economical. However, the structure will suffer some damage as explained in the earthquake design philosophy. If you remember, in the earthquake design philosophy, I was trying to explain to you that some kind of damage will always be permitted in order to make the structure economical. So if control damage can be permitted so that life is still safe in the structure, then R factor will be high because it will be in our control the damage will be properly controlled and life will be safe. This can be done only when the structure is very, very efficient, and after undergoing a lot of stress cycles, still the structure is in such a state that life safety is ensured. So only then R can be taken uh, a very high number. Otherwise, R cannot be taken. R shall be taken less. Uh, so a good example of this is when you compare a steel structure and reinforced concrete frame structure properly designed with the masonry structures. You know that in masonry, particularly in stone masonry and brick masonry, unreinforced, the damage cannot be very well predicted, and even if the structure gets damaged, uh, in some parts, it is quite possible that total structure collapses and the life is at risk. So R factor cannot be kept high or the rigid masonry structures as compared to masonry structures in flexible structures, in steel structures, or in reinforced concrete properly designed frame structures. It is possible to design the structure such that the damage is controlled after a lot of inelastic deformations, and the life safety is ensured. So in that case, we can take R factor. We can take a high R factor system. R factor is 8.5. The R factor ranges from 3.5 to 8.5. You can see that in some concrete systems, this R factor is 3, but with a good connection system, or reinforced concrete frame system, or steel system, R factor is 8.5. So when R factor is high, because R factor is in denominator, so the base shear, the result of high R factor in the denominator will be a small value of base shear, and a small value of base shear means less stresses in the structure, and less stresses means an economical structure. Then the time period can be calculated in two methods, method A and B. And method A is very simple. Time period is calculated from this equation, Ct in Hn power 3 by, depends on the type of structure. For a concrete structure, 0.03 is F. H is the height of the structure, and then time period can be calculated in this manner. Finally, the base shear calculated from the basic equation shall be greater than this, but need not to be more than this. And in zone 4, we will get this equation also. Okay, once the base shear is calculated, then the base shear will be distributed or will be transformed into a set of forces, and this set of forces will be applied at story levels in order to produce the same effect as if the structure has been hit by an earthquake at the base of the structure. So these forces are calculated from this equation. Giant force at particular level x of the structure is given by this. Fx is equal to E minus Ft Wx eject divided by summation of Wh. Demonstrate this with an example. However, you need to understand W is weight of the story, H is the distance base to the story, and this is V is the total base. FT is a applied to a top level, i.e. the roof, in addition to the Fx force at that level. When time period of the structure is more than 0.7 seconds. So if it is less than, if the structure up to 7 shape, kind of a triangle, will form a triangle type of shape like this. if this up to 7 stories. But now, if the time period is more than 0.7 second, it means the structure is tall. So in tall structure, it's quite possible that this thing has happened like include this effect of this wavy nature of displacement. The FT has been included. More force to the top stories as compared to the bottom stories. There is an example now. With this example, the application of base shear and the distribution of forces will be demonstrated. Are given directly on floors, and the SMRF we will discuss in the next week what is SMRF, but it is movement testing frame made of concrete. Given is 1 R for SMRF is 8.5. Time period will be calculated. Weights are also given, so we can calculate base shear. First of all, let's say we calculate CV. So CV corresponding to the zone 3, 0.3, and SG type style is 0.54. Is corresponding to SG type style is 2 values SD and CV and CA from these tables. CV is 0.54 and CA is 0.36. Next is the important factor. This is directly given to us. This is 1. R SMRF is taken as 8.5, correct? Time period will be calculated. Time period CTHN power 3 by 4. 0.03 into 60 power 3 by 4 is 0.646 seconds. Time period is less than 0.7 seconds, so FT will be 0. Total weight of the structures comes out to be 3900 kg. Now we can apply the base shear formula, which is CVI divided by RTW, 0.54 into 1 in this. So V comes out to be 383 kg. Then this need to be checked against the maximum base shear, so 2.5 CA I divided by RW, which is 413 kg. The total design base shear shall not be less than the following. This one. The base shear that we have calculated from the basic equation is within this range of 413 and 154 kg. So this base shear is acceptable. Vertical distribution of base shear to stories. The joint force at a level x of the structure is given as Fx is equal to U minus FTWx. I range is from 1 to n. Ft is additional force. It is in this particular case equal to 0 because time period is less than 0.7 second. Okay, first of all, let's say calculate the summation of WIHI. $800 multiplied by 36 plus 860. So this comes out to be 138,008 K. Summation of WIHI is calculated. Ft is 0. So this will be 383 minus 0. For story 1, F1 here at this location will be 800 into 12 because it is WX HX. So HX means 800 into 12 multiplied by 383 minus 0 and divide by this 138, which is common for all the labels. So in this manner, we can also calculate F2. F2 can calculate in this manner. 383 minus 0 into 800 into 24 and divide by this. Similarly, other can be calculated, so they can be produced in a table like this. With the story 5, the top one, maximum force is 116, 107. And if you look at the forces varies in the in terms of the heights. 27 multiplied by 2 almost equal to 80, multiplied by 4 is this, multiplied by 5 is this. So all these values are given in this manner, okay, and the total base share must be equal to 383K. Any question? Okay. So we'll move ahead with the structure in this manner. And now you can analyze the structure along with the gravity load. So this will be, if these forces are applied, this will produce some stresses. Bending moments, and these bending moments can be then added to the bending moments, and then okay, this was enough. This is enough for today. If you have any question, you can ask for questions. Otherwise, the remaining part of the lecture will be covered in the next week. Because we have a meeting now in the university. So if there is any question, you may ask your questions now, please, or even in the previous lectures, if you want to ask any question. Any question?
Excuse me, sir.
Please.
सर बाज राइट अगर सर जो ये वीक स्टोरी और सॉफ्ट स्टोरी सर
आपका नाम क्या है? नाम, what is your name?
मोहम्मद जासिम.
मोहम्मद जासिम. Okay, now you can ask your question, please.
सर बाज राइटर जो होते हैं ना सर वो वीक और सॉफ्ट स्टोरी को सेम सेंस में लेते हैं ना सर, ये सेम है या डिफरेंट है?
ये डिफरेंट है
सर. अगर थोड़ा एक्सप्लेन करें सर.
मैं एक्सप्लेन करता हूँ. सॉफ्ट स्टोरी जो है ना, उसका ताल्लुक स्टिफनेस के साथ है. ठीक है, सॉफ्ट स्टोरी का ताल्लुक स्टिफनेस के साथ है. यानी एक स्टोरी है कि उसमें आपके जो है एक बहुत बड़ा, जिस तरह के होटल में होता है कि कहीं पर कमरे होते हैं तो कमरों के दरमियान तो फासला कम होता है, और एक दरमियान में एक बहुत बड़ा हाल आएगा तो आपने कॉलम दरमियान में से ख़त्म कर दिए. समझ गए आप? तो जब आप दरमियान में से कॉलम ख़त्म करके दरमियान का एक बहुत बड़ा हाल बनाते हैं तो उधर कॉलम कम होने की वजह से वो स्टोरी फ्लेक्सिबल हो जाती है, तो वो सॉफ्ट स्टोरी है. अच्छा, ये पॉसिबल है कि एक वक्त में एक स्टोरी सॉफ्ट भी हो और वीक भी हो, ये पॉसिबल है, लेकिन ज़रूरी नहीं है कि हर सॉफ्ट स्टोरी वीक स्टोरी भी हो. सॉफ्टनेस जो है वो बिटवीन द टू स्टोरीज, जब बहुत ज़्यादा स्टिफनेस का फ़र्क हो तो जिसकी स्टिफनेस कम हो उसको सॉफ्ट स्टोरी कहते हैं, और जहाँ पर स्ट्रेंथ का आ जाता है कि एक स्टोरी की स्ट्रेंथ दूसरे कम है उसको वीक स्टोरी कहते हैं. तो बाज़ वक़्त किसी एक स्टोरी की स्ट्रेंथ अगर दूसरी से कम है तो वो ज़रूरी नहीं है कि सॉफ्ट स्टोरी भी हो, बल्कि वो सिर्फ वीक स्टोरी होगी, वो सॉफ्ट नहीं होगी. लेकिन दोनों भी पॉसिबल है कि एक वक्त में एक स्टोरी सॉफ्ट भी हो और वीक भी हो. ठीक है जी.
सर थैंक यू सर.
सर अगर कॉलम की जो लेंथ है वो शॉर्ट हो तो फिर भी सर सॉफ्टनेस आएगी ना?
कि कॉलम की लेंथ कम हो तो क्या होगा?
सर लेट्स सपोज अगर हमारे साथ 2 स्टोरीज है ना, तो एक स्टोरीज के कॉलम लेंथ 10 फीट है और दूसरे वाली की 8 फीट है, तो अभी 8 फीट वाला जो है वो सॉफ्टनेस क्रिएट करेगा ना सर?
8 फीट वाला नहीं, 10 फीट वाला सॉफ्ट होगा, क्योंकि 10 फीट ज़्यादा फ्लेक्सिबल तो 10 फीट वाला है ना. 8 फीट तो स्टिफ होगा.
ओके सर, ओके.
8 फीट तो स्टिफ होगा ना, 10 फीट ज़्यादा फ्लेक्सिबल होगा. ठीक है, ओके.
ओके सर.
جی گڈ کوشچنس. اینی ادر کوشچن؟
سر یہ پریویس سلائڈ پہ تھا سر، اس کے ساتھ تو تھوڑا ریلیٹڈ نہیں ہے سر. ایک پاؤنڈنگ ایکشن ہے نا سر، مطلب ڈفرینس ان ہائٹ آف ٹو بلڈنگس، اگر وہ ٹچ میں ہونا نزدیک میں ہو دونوں.
کون سی سلائڈ پہ جاؤں؟
نہیں سر، وہ پہلے آپ نے ڈیفائن کیا کہ مطلب دو بلڈنگ
پاؤنڈنگ
کو
آپ پوچھیے، آپ کوشچن پوچھیے. پاؤنڈنگ ایکشن پوچھیے.
یس سر، پاؤنڈنگ ایکشن سر اس کا تھوڑا سمجھ نہیں آتا ہے.
پاؤنڈنگ ایکشن اس کو کہتے ہیں نا کہ اگر آپ نے ایک جگہ پر بہت ساری بلڈنگز بنانی ہے، جس طرح کہ آپ لوگوں نے بعض جگہ پر دیکھا ہوگا اپارٹمنٹ بلڈنگ لوگ بناتے ہیں نا، تو اس میں کئی سارے ٹاورز ہوتے ہیں. تو وہ تو اس میں ٹاورز اگر ایک ٹاور اور دوسرے ٹاور کے درمیان فاصلہ بہت کم ہو تو اس میں دو ٹاورز ڈیورنگ ارتھکویک ایک دوسرے کے ساتھ ٹکرا سکتے ہیں، اور اس ٹکرانے سے ایک دوسرے کو نقصان پہنچا سکتے ہیں. اس کو پاؤنڈنگ کہتے ہیں، اور پاؤنڈنگ سے اسٹرکچرز کو بچانا ضروری ہے. ابھی ہم ایک ڈیزائن کر رہے ہیں اسلام آباد بحریہ فیز 7 میں. اس میں ہمیں یہ مسئلہ پیش آیا تھا. اس میں 40 کنال میں 4 بلاکس تھے، تو اس میں زیادہ گیپ ہم نہیں رکھ سکتے تھے، کیونکہ اس میں اگر آپ زیادہ گیپ رکھتے ہیں نا بٹوین دا بلڈنگس تو اس میں لینڈ ضائع ہو جاتی ہے، اور بھی کچھ مسئلے ہوتے ہیں. تو اس میں وی الاؤڈ پاؤنڈنگ بٹ دین وی ڈیزائن فار پاؤنڈنگ. اوکے، ٹھیک ہے، سمجھ گئے میری بات؟
یس سر، اوکے، تھینک یو سر.
پاؤنڈنگ سے کیا ہوگا کہ اسٹرکچر کنکریٹ کرش کرے گا نا، تو آپ اس کے لیے ڈیزائن کریں کہ کرش نہ ہو. باقی تو ٹکرائے گا، کیونکہ جب قریب ہے تو ٹکرانے سے تو آپ روک نہیں سکتے. درمیان میں ہم کوئی ڈیمپر مٹیریل لگا لیتے ہیں، وہ فلیکسیبل ہوتا ہے، اور اگر اس سے امپیکٹ زیادہ ہو جائے تو اس کے جو قریب بینز اور سلیبز ہیں اس کو ہم ایسے ڈیزائن کرتے کہ وہ کرش نہ ہو. اینی ادر کوشچن؟
سر یہ آپ نے کہا کہ ٹائم پیریڈ کو ہم جنرلی 0.1 ملٹیپلائی نمبر آف اسٹوری سے بھی کر سکتے ہیں.
اپروکسیمیٹلی میں نے کہا.
سر آپ نے جب یہ ایگزامپل تو 5 اسٹوریز ہے اور اس میں تقریباً 0.6 سمتھنگ آ رہا تھا.
ہاں ٹھیک ہے.
تو سر یہ
وہ تو اپروکسیمیٹ ہے، نہیں بہت زیادہ نہیں ہے. کیونکہ اگر آپ اگر آپ اس کے لیے معلوم کریں نا بیس شیئر تو کوئی اتنا فرق نہیں ہوگا. آپ بیس شیئر معلوم کریں with this time period in the denominator, it will not bring too much difference in the base share.
اوکے سر.
لیکن اگر ڈفرینس آتا بھی ہو نا تو آپ 0.1 ٹائمز نمبر آف اسٹوریز سے پریکٹیکلی معلوم تو نہیں کرتے ہیں نا، وہ تو ایک اسٹیمیٹ ہے. ٹھیک ہے، آپ تو یہ میتھڈ جو کوڈ میں دیا گیا ہے اس سے آپ معلوم کریں تو آپ کا ایکوریٹ ہوگا. آپ کو 0.1 سے معلوم کرنے کی کیا ضرورت ہے؟ وہ تو ہم صرف آپ کو ایک کنسیپٹ ایکسپلین کرنے کی کوشش کر رہے تھے، آپ اس سے معلوم نہ کریں.
اوکے سر.
ٹھیک ہے. Any other question? یہ پچھلا جو ہمارا لیکچر تھا ڈی ڈی ایم والا وہ صحیح سمجھ گئے تھے آپ لوگ؟ اس میں تو کوئی ایسی مشکل بات نہیں تھی. اس کا پنچنگ شیئر اور فلیکچر پارٹ دونوں. آئی ہوپ دیر واز نو پرابلم، کیونکہ لیکچر میں کافی ایکسپلینیشن موجود تھی، تو آئی ہوپ کہ آپ سب چیزیں سمجھ گئے ہوں گے اس میں. ٹھیک ہے.